with the deflection curve already obtained, we are now going to plot it. Now, because this problem, let me remind you, it involves a parameter A. Okay, this A here is symbolic, so it appears in the solution as we see it. So how are we going to plot something with a parameter? Well, we're going to use a so-called slider in this case. So we'll explain what the slider is as we go along. So let's now go back to the calculator where we obtained solution. Okay, actually let's put it in something called SOL, okay, or SOLN. Solution is what comes out of the solve command. Okay, because at this point EIY, you see, contains the unknowns. Okay, it looks actually rather simple. I prefer to look at it this way. Okay, in two steps. First, it's in terms of X and the unknowns, and then I have another solution for the unknowns. So with these two steps, it's a complete solution. So now let's define some numerical substitution rules. So it's called an num. These will specify the constants for the beam. L is going to be 3 meters. And E, the Young's modulus, will be 11 gigapascals. So that's in standard units, 11 times 10 to the 9th. And by standard units, I mean meters and newtons and so on. So I is going to be, okay, put in an equal sign here. I'm building an equation to specify all the numerical properties of the beam. So I equals 1.5 times 10 to the minus 5th power. That's actually in meter to the 4th units for the moment of inertia. And the load is 1.8 kilonewtons per meter. So the symbolic Q will be replaced by 1.8, okay? Or I can just write 1800, okay? So that's what's specified here in the notes. So I put these numbers into a numerical substitution rule. So now let's build something called Y_num, okay, Y numerical. It's going to be EIY, of course, that's not good enough because it carries E and I. So first I need to divide by E and divide by I. But these are just symbols, right? So if you just put it in like this, there's no number being entered. So we need to substitute num, okay? And of course the solutions, but let's do a step-by-step to see. So here, the beam properties and Q have become numerical. However, I still have those unknowns, unknown reactions, for example, RA. So actually we need to do one more substitution, which comes from the solution to the unknown reactions. So now you see it's almost ready to plot because this numerical deflection curve contains the variable X and also just one unknown or one parameter left, I should say, which is A. Okay, so you cannot plot something like that because A is just a symbol. So first, let's do one extra step. Okay, Y plot is going to be this Y_num with A replaced by AA. Sorry, replaced by AA, just to keep another version of it in case you need to go back to Y_num, okay, for other purposes. So let's just prepare something for plotting. But at the same time, I would like to multiply it, okay, to some step functions to trim it. This is not done in the notes, but let me do it at this point. So let's multiply to h of x so that when x is negative, nothing appears. Also, I need to deduct by x minus length, okay? The length is 3, x minus step function for x minus 3 will do it, okay? So this is done to trim the end, okay? I don't want any plot when x is negative, so the h of x will take care of that. I also do not want any plot to appear when you go outside the beam on the right-hand end, which is at 3 meters, okay? So that's my y plot. At this point, you know you have no more integration to do, so you can define h of x now for plotting purposes, okay? And that, by the way, destroys the symbolic nature of h. So it's when x is smaller than 0, give me 0, otherwise give me 1. That's a step function's numerical property. Let's give it to the calculator. Now if you look at y plot again, okay, it's almost plottable now because there's no more h, but AA is a parameter. So one thing I did in the notes, which I'm not going to do here, is I checked its correctness, okay, against a handbook value for the midspan deflection, but you can do that yourself. Okay. So let's turn to the next page of the notes. Let's try to plot this thing called y plot and see what happens. Okay, to do that, you need to insert a graph. So press document key, insert a graph under the same problem, okay? And let's do y plot. Oops. Now this calculator is smart enough to know that in this situation, you may need to create a so-called slider for the actual numerical value to use when you plot it, okay? Because this expression you're plotting contains a symbol, AA. So yes, let's create it. And you can right-click here for the properties. Well, what is AA? It is the length at which the load disappears. So it has to be smaller than 3, okay? AA, the maximum value of AA is 3. That means the UDL occupies the whole beam. And the minimum value is 0, okay? So value means the first time it appears, okay, we can use 1. Or maybe more like the diagram, maybe use 2, okay? Minimum is 0. And maximum is 3, we know. Step size, perhaps automatic, or let's go at 0.1 meter intervals. Okay. Oops. If you're using the handheld version, you can use the tab key, okay, to tap and go around. But here I have a mouse on my computer version. So, okay. So now you are plotting the deflection curve with an AA value of 2. Let's do a zoom. Fit. All right. One thing I don't like is this value is too small because it's been plotted in meter units. Let's return to the calculator. Let's do one more thing. Let y plot equal itself times 1,000, so that we are plotting in millimeter units. Okay. Now it goes off the chart. So let's do a zoom again by fit option. So we see, okay, or you can zoom by a box, or go by window settings. The minimum for X, let's give it just a -1. That's good enough. The beam is 5 meters long, so maybe you can give it a 8. Okay, X scale 1. Y minimum, you see some hints. Okay, the worst it gets is this much, so maybe give it a -5. Okay, it never goes positive because we're pushing down on the beam. There's no reason for it to bounce up. So Y max, let's give it just maybe 1. Okay, Y scale, perhaps just 0.1 units. Okay, so you see, that's what happens. Actually, let's do analyze graph and get the minimum. Okay, you need to give it lower bound, upper bound. Actually, let me do it again. Menu, analyze graph, get the minimum. When you choose the lower bound, go to the left of the beam. So you cover the whole beam. Okay, and when you pick the upper bound, go outside the beam. This way, when you change A, this analyze graph function remains valid. Okay, what you have done remains valid. So we see the worst deflection is 1.85. 1.85 millimeters. What you can do, of course, is change the value of A. Okay, you can grab it and change it. Oops, it doesn't. Oh, yeah, that's the problem because Y plot is entirely numerical. Let's try and fix that. Okay. So what you should do is go back to the beginning because I fixed it too late. Okay, so Y plot should be this. Y num with substitution for the symbol A and multiply to 1000 at this point. Now, there's also a problem because once you use a slider, you see now AA appears in boldface. That means it's a number, okay? So what we should do is first delete variable AA and then do this. Because when you're using the slider, you're assigning numerical values to AA. So that it's no longer symbolic. So now that you have turned it symbolic again, let's do this again. Okay, so that's better. Let's go back to the plot. And give it some settings again. Let's make it appear at 2. Okay, now it should work. You see, this is nice to control. Yeah, let's expand the window a bit or zoom in a bit. I don't know why I chose 8 meters. Okay, we have only 3 meters of beam. So let's give it a 5. Actually, let's make it better. Let's go from just minus 0.5 to plus 3.5. That's good enough to show the whole beam. So now what I'm doing is I'm checking the effect of the amount of beam length that the UDL occupies. Of course, when AA gets bigger, I expect the deflection to be bigger because I have totally more load on the beam, right? Because Q is multiplied to A. Although Q stays the same, A changes. So you get more A, you get more load on the beam. You expect bigger deflection. Let's check that's indeed true. When you lower AA, okay, what you're lowering is the amount of occupied length along the beam. Okay, when you have just a very small portion of the beam being loaded, then the deflection is quite small. But you see the deflection is continuous. I mean, it's everywhere. The whole beam will deflect, okay? Not only the part before AA. That would be very strange. What if you bring AA to its maximum possible value, which is 3 meters? Well, then you just get the total, I mean, the whole beam being under a UDL, and that's the result, okay? So these are various things that you can check, okay? For example, I checked before that if A is L, A is 3, okay, which is the case I'm plotting now, according to some handbook formulas for the deflection, it should deflect 2.3, okay, millimeters, or negative 0.0023 meters, which we see here, okay? But this is more than a table because you can actually see how the length A affects your response, okay? So the input-output relationship is more transparent. This is when the whole beam is loaded. When let's say half the beam is loaded, then you get some asymmetric. This is not symmetrical, okay? Of course, it's not symmetrical because the load is not symmetrical, so the deflection is not symmetrical. It's kind of more focused on the left, okay? Let's actually do a more careful check. Let's do an analyze graph again, minimum. Yeah, it's the same answer, okay? So in that case, your deflection is about 1 millimeter or 1.2 millimeters downward. It's always downward. It happens at 1.33. That's not the midpoint anymore, not at 1.5, but slightly to the left, right? And that agrees with your intuition, right? Intuitively, what would you expect in that case? In what case? When A is 1.5. What does that mean? That means only the first half of the beam is loaded. Of course, that's not symmetrical, right? That means when you only load the beam, okay? You only load the beam for half of the beam length. Then, of course, you expected the deflection to be something like this, okay? With the maximum deflection actually happening before the half or the midpoint, okay? So anyway, that's the end of this video. So let me stop the video.